Hello everyone, welcome to Oracle CloudWorld. My name is Ali Mukadam and I'm a cloud solution architect with Oracle. T Today's session is about using ingress controllers and OKE. And the session is going to be divided into two sessions. In the first part, we're going to look at Kubernetes services. And in the second part, we're going to look at how to use ingress controllers in an OCI environment. So let's get started with Kubernetes services. As you know, applications are deployed in containers running in pods. Now, when a pod is created, it gets its own non-static IP address. Each of these pods might be running on a different node, and each node will have a different IP address. The pod's IP address and the node IP addresses are different. So and just as the pods are modeled, the nodes can similarly the worker nodes can similarly crash, and therefore we can rely on neither of their IP addresses. In order to have something more reliable, what we do is we use a resource called a Kubernetes service. A Kubernetes service is basically an abstraction to expose an application running on a set of pods as a network service. It is assigned an IP address, and as long as the service exists in the cluster, its IP address does not change over its lifetime. Therefore, it can be relied upon by other pods and other services that wishes to invoke it. A Kubernetes service also helps you to avoid port collisions, particularly if some pods or applications might be using the same port numbers. There are four types of Kubernetes service. They are cluster IP, node port, load balancer, and external name. The first three, they are inbound, and external name is outbound. For today's session, we're going to look at the first three and how they are used together with the ingress controllers. So a cluster IP is a default Kubernetes service type. So that means if you don't specify the service type, one of cluster IP will be created. Think of the cluster IP as a load balancer, but within your cluster. When a request lands at your cluster IP service, it will forward the request to the appropriate pod that's running your application. Now, the cluster IP, it has a cluster internal IP address on it. So this means that it's only reachable within the cluster. If you are somehow on the cluster, maybe on the worker node or on the pod, then you are able to reach that IP address. The service is also assigned a fully qualified domain name inside the cluster. So the way to reach the service is to use the service name, namespace, the service, the cluster, the domain. How does the service knows which pod to target? Well, essentially it uses label, and the label tells the service for which pods and which pod IP address it should send the request to. Now, as I mentioned, a cluster IP service is accessible within the cluster only. If we want to expose our application to the external world, that's not very helpful. To do so, we use another type of service called a node port. A node port service is basically a primitive way of exposing the service to an external traffic. And what it does is that it exposes the IP, the service on each node IP at a static port. Any traffic sent to this port or on any node, regardless of whether the node is actually running that application pod or not, is forwarded to that service, and the service eventually redirects, the traffic to the right pods. The available port range for the node port is between 30,000 to 32,767. That means the maximum number of services available on a cluster is 2,000 767. As long as you're able to reach any of the node port IP addresses and the range of node port, you're able to reach a node port service. Now, the problem with this is that just as your pods can die, your node port can also crash, or you might need to do some kind of maintenance, or you might need to scale it out or scale it back in. Therefore, we cannot necessarily rely on the node port IP addresses either. Um, Now, when you create a service of type node port, one thing to note is that one of cluster IP is automatically created for the node port service. To expose a better way of exposing an application to the outside world is to use a load balance service instead. That's the standard method to expose your service to the outside the cluster and the network. The way it works is that when you create a service of type load balancer, your infrastructure provider, typically a cloud provider, will provision a layer 7 or a layer 4 load balancer for you. This layer 7, this infrastructure load balancer handles the initial request and then sends it to your worker node where the kube proxy component is running. The kube proxy component send it to your internal cluster IP service and eventually onto the pod. In this way, you have one single IP address to handle. You don't need to expose all the worker nodes externally to the network. When you create a service of type load balancer, a service of type node port, and by extension, a service of type cluster IP is automatically created. Now, the way to think of this, of the load balance service, is a bit like the ring of power in Lord of the Ring. One service to rule them all, one service to find them, one service to bring them all in, and the cluster bind them. So let's recap a little bit about what we have learned around Kubernetes service. First, we have a cluster IP address. It's accessible only from within the cluster. And you can use it. You can use kube proxy for debugging purposes, but for all intents and purposes, it's meant to be used from within the cluster only. If we want to expose our application outside the cluster, we have to use node port. This makes the application accessible externally, but it is an administration nightmare. Not to mention, it is quite an insecure posture by virtue of having to expose all our worker nodes publicly. A load balancer is the recommended way to expose the services. However, it can be costly, and there can also be service limit to the number of load balancers you can create. Given this situation, how do we therefore expose our application to the outside world, especially if our application consists of many services? The way to do this is to use an ingress and an ingress controller. So let's look at what an ingress is first. An ingress is basically a collection of rules that determine how external clients access services in the cluster. It provides basically a layer 7 HTTP routing and load balancing. This can be based on host. For example, here I want to access www.acme.com, and I want to make sure that when I'm using this URL to access the application, my request get directed to this set of pods. It can also be based on path. So in the second use case, I'm now using the same domain, but I have a /support at the end. and I want to ensure that when I use this URL, I'm going to land, my request is going to land on this set of pods. And then finally, you can combine the two. So for example, here I'm changing the base domain, but I don't have any underlying part. But you can imagine that on the blogging site, each post will have its own URL, and we want to make sure that for every request is going to land on the set of pods that's running our blogging application. The other thing that Ingress can do is to determine how to handle SSL. You can either do SSL termination, and you can do SSL pass-through. We're going to look at this a little bit later, and an Ingress is basically implemented as a Kubernetes API resource. It's a first-class citizen now in Kubernetes, and it's got its own API. Now, I mentioned Ingress is just a collection of rules. They do nothing on their own. They don't do the actual routing. They just help something else do the forwarding of the request. And that's something needs to watch for changes to ingress resources, especially if we are defining new ingresses. And that's something need to use the existing ingress rules that you have defined to route incoming traffic to the appropriate services and eventually onto pods. That's the purpose of the ingress controller. Basically, an ingress controller is any system that is capable of reverse proxying. And it is usually deployed as a load balance service, although there are use cases where you might want to deploy them as node port. Let's look at an example. So we've got our pods over here. So one for the website, one for the support site, and one for the blog. Each of them have their respective cluster IP services, and sitting right in front of them to handle the incoming traffic that are the ingress controller pod. In this case, they are nginx. Note that the ingress controller pods are still running inside the cluster on the worker nodes. Now, what's happening is that we deploy the ingress controller as a service of type load balancer. Because of this, the infrastructure provider, in this case OCI, is going to create an OCI load balancer automatically for you. Your request come in, lands at the OCI load balancer, and as far as the OCI load balancer is concerned, its own backend consists of your worker nodes. So it sends the traffic, the incoming traffic, to your backend, and your traffic lands on the ingress controller node port, and the ingress controller pods from there handles the routing the traffic. In case you're accessing www.acme.com, it will land via this service and this set of pods. For support, it will land here, and for blog, eventually it will land on here. Doing it this way, you can see that we can scale our various applications differently. For example, our website is pretty important, so we want to make sure that it's got enough a sufficient number of pods to service all the requests. Support is necessarily important for our customers, so we want to make sure that similar to the website, our customers are able to get in, and there's no latency whatsoever. Blog, maybe it's not that important, even if it's down or takes some time. There's no need to scale it out. This is just an imaginary scenario, by the way. What if we get a request and we don't find a path for it? This is for the default the default backend. The nginx-ingress controller allows you to specify one such default backend. It's a kind of a catch-all in case you need to handle requests. You can customize the look and feel of this if you want to. Like instead of giving a blank full error. Excuse me. How do we define ingresses? So um, basically, an ingress, as I mentioned, is a Kubernetes resource. You specify, you set the kind to be ingress, and then you specify the rules. In this case, it is host-based, www.acme.com, and the path is just a slash. And what we want to do is when we get such a request, we send we want the traffic to be routed to the Acme website service. Similarly, for support, now what we do is we have one which is named Acme support. The host is the same, acme.com, and in this case, we want to add a slash support at the in the path. So by combining these two rules, we are able to distinguish the requests that are looking to access support and send it to the Acme support instead of sending it to the Acme website. Note the port numbers are the same, so that allows us to avoid port collision. Now, may possibly because the Acme support application or service is not expecting a slash support at the end. So what we can do is just do a rewrite target. What we'll do is that when the request eventually land on the Acme support service, it strips out the support. And then finally, we can, as I mentioned, we can combine the two of them. In this case, we're changing the host, but we decide to keep the path the same, and we send the request to the Acme blog service. Now, this is how we define ingress rules. As I mentioned, we need to the ingresses, they don't do anything by themselves. They need an ingress controller. So, and I also briefly mentioned the nginx-ingress controller. So let's look at how we choose ingress controllers. Basically, the way you go about picking one of them is looking at what kind of protocols your services require. There are quite a few ingress controllers out there. So we need to look at what it is, what kind of application, what is our use case. So in case of reverse proxy, the nginx and traffic and haproxy are pretty popular solutions. If your application is more of a type of, an API use case and you want to run your own API gateway, then the emissary is from CNCF is a good option to have. And that's assuming you want to run your own API gateway. If you are more angling towards a microservices kind of deployment, typically the one which is based on Envoy, in this case, Istio's service mesh is based on Envoy, tends to be favored among developers. Or you might have some other need, maybe it can be mandated by your organization. Regardless of your use case, evaluating each and every ingress controller is a time-consuming task. So the folks at KubeDex, they have done a lot of the initial hard work for you, and they have put the results in this Google spreadsheet. They go down, the analysis look at various protocols and what kind of you know, what kind of features they have. At least it can help you narrow down your initial selection for a more detailed analysis. Most users tend to start with the community Ingress Nginx. It's open source, it's community maintained, it's well documented, it's regularly updated, and packs a lot of features. That being said, it's not necessarily painless, as the author of this post paints, right? So it's a very uh, very useful and entertaining read. Now let's look at how, when you deploy your Ingress controllers on OCI, what are your options? What are the design choices you need to make? By default, when you create a service of type load balancer, including Ingress controllers, a load balancer is going to be created for you. This load balancer is actually created by the OCI's or OK's cloud controller manager. This is standard functionality. On OKE, the load balancer, the default one is public. So that means there's no service annotation that is needed for you to indicate that this load balancer is public. The load balancer talks directly to your worker node and uses them as its backends. Because it's public, it will have a public IP addresses, and therefore it needs to be on a public subnet. Now, you can also make your load balancer to be private. Therefore, when you deploy your Ingress controllers, you can make them to be private as well. However, this is not the default by CCM. You need to explicitly set a service annotation. The annotation you need to set is OCI load balancer internal, prefixed by service at Kubernetes, the beta Kubernetes.io, and the value you set is true. Doing so marks your load balancer to be private. Now, this will prevent your load balancer from having a public IP address. Now, a load balancer in OCI, a private one in OCI, can exist both in the public and a private subnet. In the OKE module that we maintain on GitHub, instead of giving the users the choice or making this confusing, we make it explicit rather. So users know that a load balancer created in a private load balance subnet is meant for private consumption only. And in doing so, you can also control who can access the services. Note that the CCM, there's another annotation that allows you to override the default load balance subnet, because at the time of creating the cluster, one of the parameters you need to provide is your default service load balancer subnet. Typically, you would use the public ones. However, if you need to deploy one in the private subnet, you can override this using the annotation. Similar to public and private, you can choose between an HTTP load balancer and a network load balancer. The HTTP load balancer, that's the one that is provisioned by default by CCM, by the Cloud Controller Manager. So you don't need to do anything. All you need to do is set your service to be of type load balancer. And an HTTP load balancer is going to be created for you. It operates at layer 7. There's no need for any additional annotation for its provisioning. And you can protect it by WAF if necessary, if that's something you're interested in. This protection can happen at the edge, and it can also happen at the load balancer itself. There are various listeners available for the HTTP load balancer, including TCP, HTTP, HTTP2, and HTTPS. In contrast, the network load balancer, that's not the default load balancer provisioned by the Cloud Control Manager. It operates at layer 4, and you must explicitly use an annotation to set it to the network load balancer. So the annotation to use is load balancers type. The value, you set the value to NLB, and you prefix the whole thing by ocr.oraclecloud.com. The network load balancer, if you want to add some additional protection to it, you can put the OCI network firewall in front of it. You can't necessarily use the WAF in this case. You can put the OCI network firewall at the perimeter. And the listeners available in this case are only TCP and UDP. Remember, the network load balancer operates at layer 4. Once you've finished choosing the type of load balancer you need, the next thing you can choose is your load balancer shape. There are basically two types of shape. One is dynamic, and they come in these buckets: 10 Mbps micro, 10 Mbps, 100 Mbps, which is the default one, 400 and 8,000. So if you just set the service of type load balancer, the one dynamic and giving you bandwidth of 100 Mbps will be created by default for you. There is also the flexible load balancer, and a flexible load balancer basically allows you to set the minimum and the maximum bandwidth, and in doing so, you get charged accordingly. So it's presumably less expensive than the dynamic one. Note also that we have made an announcement. If you have logged into the OCI console recently, you would have seen this announcement that the dynamic load balancers are being deprecated. So it would be good. It would be good if you can start planning your move to start using the flexible instead. There are two important differences between flexible and dynamic, and this is important, especially if you're going to be you're going to be creating new load balancers from now. If you create a dynamic load balancer and you need to change the shape, they require destroying and recreating. And therefore, the IP addresses of that load balancer might change unless you're using reserve IP. Similarly, or rather, in contrast, a flexible load balancer, you can change the bandwidth dynamically without having to destroy and recreate the load balancer. And in doing so, you can maintain its assigned IP address. Now, once you have use your load balancer to your ingress control to create your load balancer, it's got a public IP address. Your application is publicly accessible, and we want to make it easier for our users to access it. And to do that, we are going to do a DNS integration. Now, you can integrate this with any DNS provider. In this case, we're going to look at OCI DNS. How do you integrate the two? Well, the easiest way if you're not going to change this very often, is to use a manual method, which means that if your zone is defined in OCI DNS, you can add an A record in by the CLI, the SDK, the OCI console, or even Terraform. However, a better way is to use the external DNS. External DNS is a Kubernetes sub-level project, and it automates the creation of DNS records inside your DNS. The way it works is that it listens to ingresses being created, what kind of host is being assigned to or to, to these services, and then it makes a CRUD request to your OCI DNS. And because doing that, it requires user principal, um, for authentication purpose. I talk about this in the article, how to configure the external DNS. We do have a more secure option to handle this, and this is done via instance principle. We have a PR open for the last couple of years with the external DNS project. Please help us by voting it so we can get it merged and make your use of external DNS more secure as a result. Now, you can also use multiple ingress controllers inside the same cluster. Why you want to do that? Basically, you are interested in using different ingress controllers, like for example, ingress nginx, traffic, contour, etc. And one of the reasons to use different ingress controllers is to select the most appropriate controller for your services or application. For example, in the Verzano container platform that we are developing in open source, we use Ingress Nginx for the system, whereas the application use Istio, which is Istio's Ingress Control Gateway, which is based on Envoy. So system services such as the OpenSearch, Grafana, Prometheus, the Verizon console itself, they use the Ingress Nginx, and you can configure them so that they can be accessed internally, whereas your applications you might want to expose them publicly. So having different ingress controllers means you can secure them or place them or use different type of load balancers for both of them, either publicly or privately or both. And you can configure using public and private DNS depending on your deployment model. Another reason is to deploy different. Another reason why you want to use multiple ingress controllers is you want to deploy different instances, but instead of different ingress controllers, you're going to use the same controller. Maybe you have some applications, different applications that are running inside the same cluster, but they are being operated by different teams, or they might need more bandwidth. So you might want to choose different set the bandwidth shape to be different. Or you might want to expose certain services on a private network only. For example, one customer, what they wanted to do was they wanted to ensure when their users access their application from an office or via VPN, they have just a normal username and password login. Obviously, still secured with HTTPS. But if they are accessing outside the and not in VPN, they need to key in. They need to use two-factor authentication. So all controllers must be when you have multiple controllers inside the same cluster. There might be a competition for between the controllers to serve the request. So therefore, all the controllers must be aware of which ingress they serve and then which one they have to ignore. And the way to do that is by using ingress class name. So the way the ingress class name works is that when you deploy ingress, any ingress controller, you will set this class name. For example, here this one has web, this one has blog, store, and support. When you create your ingress, you will set this ingress class in your ingresses as well. This ensures that only an ingress controller that has this class name will respond, will handle the request. The others will not try to attempt to handle requests of type whose ingress class name is of type web. Likewise, the blog will be handled by this one, and the store application is handled in this case by the haproxy, and eventually supported by the contour. This is a trivial example of how ingress class name work, but you can imagine how you can use this to making sure that certain applications are handled by certain ingress controllers, and by using annotations you can control their accessibility and visibility, either public or private, or set certain bandwidth parameters, etc. Okay, now let's now look at SSL termination, so and as well as SSL pass-through. So typically there are a few use cases. So in this case, you have the HTTP request that terminates at the load balancer. This load balancer decrypts with a key that is the client still sees a key associated with this load balancer, and the load balancer forwards the request to the ingress controller, which then decrypts and sends an HTTP. It re-encrypts it with its own key and sends it to a service of type of cluster IP. This is similar to the traditional, end-to-end load, end-to-end encryption. Why we wanted to do the decryption here is because we may want to inspect the headers. Maybe you want to do some modification. Maybe you want to put the load balance in between. So something like this we might want to do. And the implication here is that we don't trust this network, the cloud provided network, and therefore we want to do our own encryption. A variation to this is that the SSL terminates at the load balancer, and then we trust this network. Maybe because this application is going to be accessible, is going to be accessed internally only, or maybe it's not. You think this traffic, the rest of the traffic internally is not required to be encrypted, regardless of your need. In this case, the SSL request terminate here, and then the load balancer forwards it on to the ingress controller, which then sends it to the cluster IP inside the cluster. A third one, and this one is the most common use case, is that the load balancer receives uh, the HTTPS request. It functions as a reverse proxy and then sends the HTTPS traffic to the ingress controller. Where the traffic gets decrypted, and from here, remember the ingress controller itself is running as a pod on inside the cluster, so it's sent into to the cluster I to the cluster IP services inside the cluster. A last variation to this is to use SSL pass-through. In this case, we're going to be using, instead of the HTTP load balancer, we're going to be using the network load balancer. We still receive HTTPS, but what we really see is TCP traffic. So we just send it on, and the incoming traffic lands at the ingress controller where it gets decrypted, and the ingress controller sends TCP traffic to the Kubernetes service. Note that in each of these scenarios, I'm just using nginx as an example, the nginx ingress controller as an example for the ingress controller. It's not necessary to reflect its capability in terms of the protocol security, etc. You need to do your own evaluation for this. Once you have deployed your ingress controller, you are able to secure it using the OCI web application firewall. So there are two use cases. One is you can secure it at the edge. What this means is that the OCI WAF, it has a series of endpoints that exists around the world, and we are indicating to the OCI load balancer to only accept requests coming in from the edge, and either requests that are not coming from these edge subnets, then they're going to be rejected. And when you have created the edge policies, then you need to add your own additional protection. Like, for example, capture. If you want to use captcha, you want to look at threat intelligence or bot protection. This is the kind of or you want to implement OWASP top 10. These are the kind of policies that you need to implement. Similarly, you can, if your application is running internal, like in a private, the load balancer is private only, you can still define the WAF policy to protect your application. It doesn't, in this case, you're not, there's no need to restrict from the edge, but you can still apply the WAF policies to protect your application. How do we protect our application if we're using the network load balancer? You can use the OCI network firewall, and you insert it in between the network firewall, the network load balancer that's running at the edge, at the perimeter, and you basically configure the next hop of this to be the OCI network firewall, which will you configure to decrypt and to inspect packet headers and so on and so forth. In this way, you can add additional protection for when you're using the network load balancer. Lastly, when you run your ingress controllers, you may want to also look at the performance monitoring. So there are some metrics available on the load balancer itself. But what about how the ingress controller is behaving? This is different from the OCI load balance metrics. Personally, you would expect them to have more or less the same shape, maybe. But you want to have maybe a better understanding in terms of how the ingress controller pods themselves they are dealing with it. Do you need more pods to handle the request? Do you need to have a bit more tuning? So let's look at an example. As you here, this is a graph that is generated uh, that showing the load generated by the Locust performance testing tool, and it's just we've configured to hammer a simple the Acme website service. And the average latency for the 90th percentile is 276 milliseconds, while for the 95th percentiles is 1.32 seconds. If we want to improve this, one thing you want to you can do is to use the configuring the TCP VBO. TCP VBO is a new congestion algorithm that was developed at Google. It stands for bottle bandwidth and round trip propagation time. And as you can see, it improves the average latency, and it can also improve the throughput apparently by a factor of 3 times in this case. Your mileage will vary. It will depend on your application, your payload, etc. But essentially, it can improve um, the perception of your application performance. And the package to install TCP BBR is available on Oracle Linux, and this similar to the 90th percentile, you get roughly about 50% improvement for the 95th percentile. Only in the 99th percentile, it did not record any or barely any improvement in this case. So that's it for this session on ingress controllers and its use on with OKE and in OCI. I hope you are having a great time. Enjoy the rest of CloudWorld. Thank you very much.